Okay, the material for the second midterm is everything since the material for the first, and so it covers everything from week 4, not including accelerations, but including everything we talked about Bernoulli, and the 2 conservation equations, conservation of mass and also conservation of momentum. So these are the appropriate week numbers that we have for each of those. So there are 3 questions again, each question 110 points, but top score is 100. And they relate to Bernoulli equation and manometer for the first, Bernoulli conservation of mass and conservation of linear momentum in a moving coordinate frame, and it also includes the ideal gas law, and also conservation of mass for rotational momentum. So Bernoulli, conservation of mass and conservation of momentum, both linear and rotational. So what I thought I'd do is give you the equations that I think you probably need to be able to thrive in this exam. And so maybe just a sheet of equations. Of course, you can bring your own sheet as well. But in terms of what you need to know, you need equation of state. And that is the ideal gas law, which relates pressures to densities, gas constant, and temperature. Temperature and pressures have to be absolute, as you know, and gas constant is something that usually you're given rather than required to bring, and it's different for each individual gas rather than the ideal gas constant. The manometer equations you know that the rules that are used are that if you go up, you subtract pressures. If you go down, you add pressures. The pressures are given relative to a reference pressure plus the unit weight of the fluid multiplied by a change in height. And if you are in a gas, then the density of the gas or the unit weight of the gas is small compared to a liquid, and so you can often take it to be 0. And if it's in a closed container, then the pressure you can take as the vapor pressure of that particular gas, which you'd also be given. And so I guess those are the important components that relate to that. In terms of Bernoulli's equation, we looked at it in 2 modes. We looked at it parallel to a streamline, in which case we look at behavior between an upstream and a downstream point, and we label them 1 and 2. The velocities are velocities in the direction of the streamline or along the streamline. If we think of a stream tube, then those stream tubes have areas A1 and A2. And if we write Bernoulli's equation, we can write it in terms of usually units of length, which are upstream pressure divided by unit weight of the fluid, plus the elevation head, plus the velocity head, and that is equal to the pressure head downstream, plus the elevation head downstream, and the velocity head downstream. It doesn't matter whether they're upstream or downstream when there's no energy losses, but we, as convention, this is always upstream. What else? If we need to do, if we only have 4 of these variables and we need to close the set of equation, then we can write conservation of mass, and that is just that upstream velocity times area times density is equal to downstream velocity times area times density. Often these densities cancel out, and you're just left with the product of velocity and area for upstream and downstream. And so I suppose we should note that in terms of geometry, we usually write, it doesn't matter what x and y are, but z is always positive upwards by convention. And if we do that, then we can just write behavior at two individual locations. So that's Bernoulli's equation. The conservation equations that we need would be, well, we've already alluded to one of them, and that is conservation of mass. We can write it in terms of Reynolds transport theorem, but if we go just the next step and write it out in full, then we can write the conservation equation in terms of some control volume. So some control volume, a control surface around that control volume, and the conservation equation is just the density multiplied by rate of change of volume, plus the volume times a rate of change of density, plus the sum of the mass flow rates, uppercase m or lowercase m, we've used both, I guess, and those should sum to 0. The mass flow rates are always given by a velocity out of the system. We often call that W, times the density times the cross-sectional area. And we'd include these for all of the different faces that we had in the system. And the sign convention is that, at least for these, if it's a mass rate out, then it is positive, because the flow rate in the direction of the unit normal is aligned directly with it. And if it's a flow rate in, it is negative, as this would be. So flow rate on this side relative to this outward normal. Okay? And so that's the sign convention that we just have to be aware of. You'll remember, I guess, that these expressions here come from the term which is a rate of change with time of density and volume. And so by splitting it this way, we split it up into the equal components. So this is the case where we have a volume of the container which is expanding, but the density of the liquid is not changing, and so we can accommodate that, such as filling a balloon with water, I guess would be a case for that. And this is where the volume's static and the density is changing, so I guess this would be filling up a gas cylinder with air from outside, and the air compressing and density changing as a function of being introduced into the system. We talked also about control volumes which are moving, and so I guess we need to be mindful of that. And the example we always used was the one of a water jet being squirted out of a system that's moving at some velocity of the control surface. And we know that relative velocities are, we can write that the static velocity is equal to the velocity at which something comes across the control surface plus the velocity that control surface is moving at. So this just becomes the vector sum. These are typically just single magnitudes, but they are actually vectors, of course, in x, y, and z. But if you resolve in one direction, it would be the component in the direction in which you choose to resolve. So that's conservation of mass. We talked about conservation of linear momentum. And if we look at conservation of momentum, then we have a similar expression. It also came from Reynolds transport theorem. It also operates on some kind of control volume, and that was that the magnitudes for steady state behavior that we're looking at, then we can always we sum the velocities times the mass flow rates, and those are equal to the sum of the forces that are acting. These are vectoral quantities, but the most general statement to look at, which includes this case also, is that we write it for, again, the case that we have the behavior defined in terms of this relative velocities. So we want to define forces relative to a static reference frame, and so we can rewrite this expression in slightly different form, and that is that the sum of the velocities, where the velocities are the relative velocity plus the velocity of the control surface multiplied by the mass flow rate, is equal to the sum of the forces that are applied. And in this, again, the mass flow rate is going to be the density times the area of the surface multiplied by the relative velocity as it goes across that. And the convention for this, again, is the mass rate out is positive and the mass rate in is negative. And so if we have that, then we can get a balance that allows us to be able to calculate what the forces are that's applied on the structure if we are holding it static by those forces, or if those forces are zero, we can calculate what the velocities are that that structure might move at. And we can always calculate, if we look at, for instance, magnitudes of velocities versus force. So in other words, if you look at the force that you have to apply to hold something static versus the velocity it's moving at, if you're applying no force, then something would be moving at its maximum speed. If you're holding it static, then you'd be applying the maximum force. And the magnitude of the behavior between these, if you only hold it with a small force and you have a small velocity applied, this product of these two represents the magnitude of the power that you get out of the system. So power, let's see, work is equal to force times displacement. Power is equal to force times displacement rate. In other words, the rate of displacing. And so power is equal to just the force times the velocity. And so those are the two axes that you have here. And so when you have a high force but no velocity, then by definition, the power you get is zero. And if you have zero force but a high velocity, you also get no power. But at intermediate points along this line, you'll get different amounts of power. And actually, if you plot this, as we've done certainly in the past, you could plot, for instance, velocity versus power, and plot these components. You'd find out that power would look something like this. Some peak power in here, zero power at this magnitude, and zero power here. So that's a useful expression to know, and of course the units of this are in watts, which are joules per second, which are Newton meters per second. So you just have to be aware of the units that would be applied. So that's conservation of linear momentum. If we then turn our attention to look at conservation of rotational momentum, then that is for something that is moving around an arc. This is the direction of the arrow. As it goes around the arc, it has some rotational speed, which we'll call v theta. There is a force that is applied in this direction. There is a lever arm which it operates through, which is the radius of this arm here, as it goes around this particular fulcrum. And in terms of that, the conservation of rotational momentum that we have is that the sum of the radius at which it turns, cross product of the relative velocities of the fluid rate at which it comes out of the nozzle, plus the control surface velocity multiplied by mass flow rate has to be equal to the sum of the radius cross product with the force that's applied. And this term here, of course, is the torque. Force times length is basically a lever arm. And this component here is really the static velocity, or the velocity of the head relative to, or the fluid relative to the static observer. And so these are the components that we need to be able to rationalize. Again, if we know what the magnitudes, if we hold the component static, so these are 0, we can calculate what the magnitude of the torque would be. And if we allow the torque to be 0 so it can rotate freely, we can calculate what the relative velocities of the water and the rotation are if we have some constraint on that. And if we choose an intermediate value of these forces, again like this, then we'd expect that we'd have an intermediate value of the power between these two end members of 0. And for these particular systems, again, we can calculate the power is equal to just the torque that's applied, which is this, multiplied by the rotational speed, where omega is in radians per second. It's the rotational velocity, if you like. And we can always make conversions between these such that an angular velocity v theta is going to be equal just to the radius of the lever arm multiplied by the angular velocity. So length times radians per second gives you length per time, which is the correct one for this. And we can always convert between magnitudes of radians a second and magnitudes of revolutions per second just by noting that there are 2 pi radians on the circumference of a circle. And so we can use this conversion factor, where this radians a second is basically what we're defining omega as. So this magnitude here is omega. So between those, you probably have all of the expressions that you need to be able to do stuff for this particular midterm. So the other thing we could do is we can also go through the notes. So the notes for this are online. And you can grab these just by going through to the course resources page. These are probably more expressions than you need. We've looked at some of these already. This is the Bernoulli's equation along a streamline. This is the Bernoulli's equation perpendicular to the streamline, both written in the same terminology. These are the differential components. You can use Bernoulli, as we have done, to get the equation for a free jet. We can define conservation of mass in terms of these simple terms here. We talked about relative frames of reference, and so you have substantial derivatives defined as a function of spatial derivatives, and we've talked a reasonable amount about that. We can talk about streamline accelerations. We've dealt with those. We used Reynolds transport theorem, as you recall, to be able to get a couple of things. We used it to get conservation equations for conservation of mass, which we can write a little more simply than this, which we've just written in the previous pages. We can also use Reynolds transport theorem to write the expressions for conservation of linear momentum, which we also wrote in shorthand. And we can also use the same relationship to write the equations for rotational momentum. So I'm not suggesting that you need these expressions, and also we talked about converting power in these systems from torque and rotational velocities. So I don't know that you necessarily need all these expressions, but certainly the preamble that we had here in the previous red written expressions are the ones that you really need, I think, for the exam. So just in terms of summarizing maybe some of the things we've talked about, the manometer equations, we can always get the pressures if we know what the height changes and the unit weights of the fluid by going up or down. We always start from a reference pressure, and from that reference pressure we can calculate the new pressure at a particular point as a function of how high we go up or down, where we use the appropriate manometer rules as well. Like if we go up, we subtract pressures. If we go down, we add pressures, etc. And so we certainly spent some time dealing with that. You should know how to do that. We talked about using Bernoulli's equation to be able to define changes in pressure as you go across a streamline. We didn't highlight that in the previous equations, so you might want to decide how much time you talk about normal to streamline changes in pressure. We talked about measuring pressures with pitot tubes, and the fact that in some manometer equations, if the velocity goes to zero, you'll build a dynamic pressure as a function of that, and the magnitude of that you can calculate by writing Bernoulli between an upstream and a downstream location, and we know how to do that. We talked about equations for free jets, which is just the straightforward application of Bernoulli's equation between an upstream location and a downstream location. We just have to be careful to be able to define the appropriate boundary conditions. The boundary conditions often are, if we talk about a large tank, basically means that the velocity can be thought of as zero. If it's at atmospheric and we're doing everything relative to gauge pressures, then P1 in gauge pressures is equal to zero, but P1 in terms of absolute pressures would be equal to, say, 101 kPa. And you can do the calculations either way. It's often easier just to do it in gauge pressures because then you don't have to account for atmospheric pressures. And likewise, you do the same at this point here. This is either P1 in gauge pressures, which is 0, or P2 in absolute pressures, which would be 101 kPa. The reason the pressure here at the exit would be equal to 0 gauge or 101 absolute is because the pressures acting at a point act the same in all directions, and if it's acting horizontally equal to zero pressure gauge pressure, then it has to be within the center of this orifice as well. And so in terms of velocities, pressures, and of course this relative to any datum, then this elevation would be equal to h, and this elevation would be equal to 0. So we just have to be able to define behaviors. If we do that, we can use Bernoulli's equation, as you've used many times, written this way or written in terms of a length. We tend to write it in terms of a length, which is just divided through by unit weight. I guess I've switched these, oops. I've switched these around a little bit, but you see that these are the same expressions. If we look at systems where we produce fluids, we need to just take account of exactly what's going on in these systems. If you remember, we solved this by writing Bernoulli at this point and writing at this point to calculate the magnitude of V2 that comes out of this. Large tank equation, so velocity 1 is 0, elevation of the tank is given, and the large and atmospheric pressure, so pressure 1 is equal to 0. Pressure here is equal to 0, and we know it's elevation, and so the only unknown to calculate is V2. And if we know from Newton that every body, if it's not acted on by something else, will continue to move, then we can resolve this velocity into components, not in the direction of flow, but in the horizontal component and the vertical component. We know that the vertical component will go up until it's overtaken by gravity, and it will stop, and then it will start coming down, which will give you the location of this apex. And the horizontal distance is given by the time taken to come out of this orifice to hit the ground, multiplied by the horizontal velocity of this system. So we can use those to calculate how far it would go, how long it would take to reach its peak, how long it would take to reach the ground, just from knowing something about the exit velocity and knowing that that won't change as it comes out of the system in each of these two components. So we can use that. We talked about if we have Bernoulli and we have only 4 terms and we need to constrain the system, then we can write conservation laws in terms of conservation of mass, which is just this. Densities are often the same, and so it just becomes V1A1 is equal to V2A2. And so we can relate the velocities at the inlet and outlet purely in terms of those by drawing a control volume that cuts it off at these particular locations. We can also look at unsteady problems by looking at flow rates out of a system and looking at how quickly this is replenished, for instance, and solve in time. You can go back to look at that if appropriate. We can use manometer equations to be able to look at flow velocities that are unhindered and flow velocities that are set to equal 0 by stagnation. And by looking at those and working our way through the manometer equations to work through a manometer from P1 to P2, we can get a relationship that defines P1 as a function of P2, and then combine that with Bernoulli to be able to solve for the magnitude of the height rises, or if we know the height rises, calculate from Bernoulli what the velocities would be in the system. And we've used that before. We can look at unsteady flows, and we've talked about that. If we look at control volumes, we can define control volumes in 3 forms. Either static control volumes, which fluid flows through, but they don't move and they don't deform. Moving control volumes that move but don't change in size, such as a jet engine. And moving and deforming control volumes that both change in volume and change in location as they travel. And we can use a series of coordinate systems to be able to look at those. We look at a couple of examples doing that by splitting up the conservation of mass equations. This is our basic relationship that we use here. And it really is defined in terms of looking at balancing mass rate in minus mass rate out. So if mass, or really it's actually mass rate out, mass rate in. And it's better to write it this way, of course, because out is positive. This is the positive value. and this is positive here, and this is negative. And so mass rate out minus mass rate in. If more comes in than goes out, then you net accumulate some, and the accumulation terms are the two terms here, either accumulating in a constant volume container where the density of the gas, say, changes as you pump up a tire, for instance, or putting a constant density fluid, such as a liquid, into a bucket where the volume of the bucket changes as a function of time. So those are the two end member conditions, if you like, that we can look at. And we've done some examples to look at each of those. An example where you, for instance, put a gas into a system where that system is capped off, where if it's a constant volume, then the density of the gas has to change as a function of time, and you can calculate what that rate of change of the density is, or what the final density is by just manipulating the mass balance equations. Or the converse of a system where fluid goes in at a constant density and the volume of the container changes as you begin to fill up that container, and so the control volume that you have that contains that accommodates that volumetric change. And you can use that also to be able to calculate the time taken to fill up the container just by manipulating this mass balance equation for the appropriate components. We have to be cognizant of the fact that if we have moving, deforming and moving control volumes, then we can always do the mass balance by taking this component here, which has to be equal to, we can get it from the static velocity, is equal to the out of the control surface velocity plus the velocity of the control surface, which is this expression here. Or we can rearrange this expression into this term here, where it's simply this is equal to the static velocity minus the velocity of the control surface. And so if we use this magnitude into this, then we can account appropriately from the changing behavior of the system. We did some examples with that. When we look at conservation of linear momentum, again, we can use Reynolds transport theorem. The basic expression we have is the one that we talked earlier about. We've written it as velocity times, no, not a dot product, velocity times the mass flow rate is equal to the sum of the forces, where this is a vector and this is a vector, and these are the same summations in this particular case. And we just have to be careful in terms of defining the magnitudes of the velocities that we use. A more generic expression, if you like, is really one that includes this velocity as substituted as these two components. Get rid of this, just make some space. Is equal to sum of the forces that are acting. These can be resolved in the appropriate coordinate directions, for example, where this is, importantly, this is positive out, negative in, but these are positive in the x direction and negative in the minus x direction, for example. So these, importantly, are in the coordinate systems of the xy coordinate system of our control volume, and these are in the coordinate system of in versus out. And so we just need to be a bit careful of that. The examples we did mean that we have to account for the sum of the forces. We know that the sum of the forces has to include both forces that are applied, as in this case, this reaction, but also the pressures multiplied by the areas. And so if we cut off a free body diagram that includes this particular case here, then it has pressures that are applied on this surface here, which would give us pressure at location 1 multiplied by its area. And likewise a pressure that's applied here. So the forces have to accommodate these particular pressures that are present here. Both of these pressures act in the positive x direction, and so they would both be positive magnitudes, but this force acting here would actually be a negative value. And so we have to just keep track of the sign conventions as we do these. If we deal with the case of a vane, we have to look at the relative velocities in dealing with this. So the appropriate relationship we use would be this one at the bottom. Which I suppose in its most generic state we can always write as the case we said before, and that is the sum of the velocities both coming out of the jet versus the velocity of the control surface multiplied by the mass flow rate is equal to the sum of the forces. If the velocities of the control surface is equal to 0, then this clearly decomposes to this, where this mass flow rate is always given by a density, an area, and the relative to the control surface velocity. And so in the case where this control surface velocity equals 0, then this expression is exactly this, because it reduces to this. Okay. And finally, we talked about conservation of linear momentum. The expression that defines these behaviors is basically given by, in our shorthand, it's given by this expression that, let me change it to this, that the sum of the radii cross product multiplied by the relative to the control surface velocity plus the velocity of the control surface multiplied by the mass flow rate is equal to sum of the radius multiplied by the lever arm. The radius is the lever arm multiplied by the forces. And so this term here represents the torque that's applied to a system. This represents the velocity to a static observer. And if we can figure out exactly what the magnitudes of the velocities of the control surface and the velocity of the fluid coming out of the system are, and know the radius at which it's defined, then we can equate both sides to be able to look at those behaviors. In simpler form, if you think of it, then this upper term here can be written as radius multiplied by the component of the velocity multiplied by mass flow rate is just equal to the torque, which is basically this expression here. Which is just a derivative of this, or a direct consequence of this expression here. And if we want to convert that to power, in the same way that power is equal to velocity times force, or force times velocity, then we can get power which is equal to the torque on the shaft multiplied by its rotational velocity, which is in radians a second, as we mentioned. And so all we have to account for is the fact that we have to account for the different velocities of the system, exactly the same as before. If we hold it with a torque so it's static, then by definition we can calculate a zero velocity of the control surface, and knowing what this is, we can calculate what the torque is that we have to apply. For the opposite behavior, where we have zero force restraining it, we can calculate what the velocity of the control surface is if we know what the fluid velocity is out of the system. And for some intermediate behavior, where we know, for instance, the magnitude of this torque and the magnitude of the flow rate out of the system, we should be able to calculate the velocity of the control surface, which of course would be the velocity of the machine that would be working for us. And so we went through a couple of examples, or an example to be able to talk about that. And so these are the summarized expressions. So that, I think, is basically the material that you probably need to know to show your best performance in this exam. I think we've talked about many different components, but to my recollection, the material that we talked about on these first few pages are enough for you to be able to get through with flying colours. So the stuff that's on these expressions really encapsulates what's going on, and of course if you've seen this movie, you'll have seen that it's actually uploaded onto the course's resource page. So good luck. There'll be an announcement on Angel giving you the particulars of the exam, and so good luck in showing that your best foot forward and your best performance on the exam. Great. Thanks very much.